We're going to continue on with the fundamental theorem of calculus part 1. And here we're going to use it to find the derivative of the function h of u is equal to the integral from 0 to u of the square root of t over t plus 1 dt. Now I know this is an integral, so it looks like we should integrate. We are not going to integrate because we're asked to find the derivative. H prime of u is the derivative with respect to u of the integral from 0 to u of square root of t over t plus 1 dt. And according to the fundamental theorem of calculus part 1, if I differentiate an integral, I get back the function that's integrated. And what changes is the argument goes from this dummy t to a u. So the answer here is the square root of u over u plus 1. There is nothing more to do. This next one is a little more involved. Same instructions. Find the derivative using the fundamental theorem of calculus part 1 of h of x is equal to the integral from 1 to square root of x of z squared over z to the 4th plus 1 dz. I'll start it the same way. H prime of x is equal to the derivative with respect to x of the integral from 1 to the square root of x of z squared over z to the 4th plus 1 dz. And it's almost the same. In place of z, I'm going to put a square root of x. So in the numerator, I have z squared, so the square root of x squared is x. In the denominator, we have z to the 4th plus 1, so that the 4th power of square root of x is x squared plus 1. But this is not done. The reason is that I have an upper limit that's not just plain x. Whenever that happens, believe it or not, I mean, we're differentiating, so it should make some kind of sense. We're going to bring in the chain rule. The derivative with respect to x of the square root of x is 1 over 2 times the square root of x. Simplifying, I get the square root of x in the numerator, because square root of x divides out one of those factors of square root of x in the numerator. Denominator 2 times x squared plus 1, and that's it. So in general, when we are using the fundamental theorem of calculus to find a derivative, the chain rule applies to the derivative if the upper limit of integration is anything but just plain x. What if my h of x is equal to like an x, the integral from x to a of f of t dt? I need the lower limit to be constant, not the upper limit. So what we would do is we would use a property of definite integrals and reverse the limits of integration, remembering to pull a make it negative. What if I had my h of x was like some function of x as a lower limit and then some function of x, some other function of x as the upper limit, f of t dt? Then we're going to break this apart into two integrals. We're going to go from u1 to 0 and then from 0 to u2 f of t dt. And 0 can be actually any number you want. It makes absolutely no difference at all as long as they match. All that the fundamental theorem of calculus cares about is that the lower limit is constant and that the function is defined, right, for that number. And then this, the second one's fine. The first one has limits that are, we'll call them out of order. And so then we would apply this thing where we can flip the limits and then make it negative.